I'm so glad you could make it tonight. You found Science Blanket, your quiet space for wonder. Have you ever looked at the horizon of the sea and felt like you were looking at a slow-motion dream? Tonight, we're wrapping ourselves in the science of the deep, specifically, the gentle, drifting life of ocean currents. We often think of the sea as a single, solid body of water, but it is actually a ghost of the globe, trillions of gallons of liquid energy suspended in a delicate balance between the sun's warmth and the icy void of the poles. From the high, warm surface streams that look like pulled silk to the heavy, cold blankets of the abyss that bring life to the floor, currents are the visible signature of the planet's invisible movement. As we begin, imagine yourself floating on the surface of a warm, salt-thick current, feeling as weightless as the water itself. You don't need to understand the physics of the Coriolis effect or the names of the thermohaline cycles tonight. Just let the slow drift of the tides tuck you in. If this blanket of water helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. Now, take a slow, deep breath. Feel your lungs expand and then empty, as steady as the tide. Let the weight of your day evaporate into the salt air. Relax your jaw, let your shoulders drop, and sink into the softness of your bed. Let's explore the quiet wonders of the ocean currents together. Beneath the surface of our vast oceans, there exists a phenomenon so powerful and so constant that it shapes the very climate of our planet. Ocean currents act like giant rivers within the oceans, moving vast amounts of water globally, in patterns that have persisted for millennia. These underwater highways carry water across entire ocean basins, connecting distant shores in ways that might surprise you. Imagine a river, but one that flows through the sea itself, carrying with it warmth, nutrients, and the very essence of life across thousands upon thousands of miles. One of the most remarkable of these oceanic rivers is the Gulf Stream, a current so powerful that it can reach speeds of up to 2 meters per second. To put that in perspective, that's faster than many people walk, and we're talking about an incomprehensibly vast body of water moving at that pace. The Gulf Stream alone transports more water than all the rivers on Earth combined, flowing from the Gulf of Mexico up along the eastern coast of North America before turning eastward across the Atlantic. Its power is both gentle and immense, a paradox of nature that continues day and night, year after year, century after century. The mechanisms that drive these surface currents are elegant in their complexity. They're driven mainly by wind and Earth's rotation through something called the Coriolis effect. The wind pushes against the ocean surface, friction between air and water setting the uppermost layers in motion. But it's not quite that simple. As our planet spins on its axis, this rotation deflects moving objects, including water, to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection, the Coriolis effect, means that currents don't simply flow in the direction the wind pushes them. Instead, they curve and spiral, creating the great circular patterns we call gyres that dominate the surface of our oceans. These currents don't just move water, they move warmth itself. Warm currents transport heat from the equator toward the poles, moderating regional climates in ways that make certain places habitable that otherwise wouldn't be. The British Isles, for instance, sit at the same latitude as frigid Labrador in Canada, yet enjoy relatively mild winters. Why? The Gulf Stream and its extension, the North Atlantic Drift, carry tropical warmth northward, blessing these islands with temperatures far kinder than their latitude would suggest. Without these warm currents, much of northwestern Europe would be locked in ice for months each year. The ocean, in its generosity, redistributes the sun's warmth, creating temperate zones where life can flourish. But warmth isn't the only gift that currents carry. Cold currents bring nutrient-rich waters that enhance marine life and fisheries, creating some of the most productive ecosystems on Earth. When cold water rises from the depths, a process called upwelling, it brings with it nutrients that have settled to the ocean floor. These nutrients, phosphates and nitrates and other compounds essential for growth, fuel explosions of life near the surface. The cold Humboldt Current off the coast of Peru, for example, supports one of the world's most productive fishing grounds. The California Current does the same along the western coast of North America. These cold waters may not be comfortable for swimming, but they're brimming with the building blocks of life. All of these currents, both warm and cold, surface and deep, are connected in a vast system known as the Global Conveyor Belt. This planetary circulation connects surface and deep currents worldwide in a pattern that takes roughly 1,000 years to complete one full cycle. Warm surface water flows toward the poles, where it cools, becomes denser, and sinks into the deep ocean. This cold, dense water then flows back toward the equator at depth, eventually rising again to the surface to begin the journey anew. It's a circuit of almost unimaginable scale, linking every ocean basin, every sea, in a single interconnected system of perpetual motion. The amount of heat that these currents transport is staggering. Ocean currents transport far more heat than the atmosphere itself. While we often think of wind and air temperature when we consider climate, it's actually the ocean doing most of the heavy lifting when it comes to moving warmth around the planet. The ocean has a much greater capacity to hold heat than air does, and these currents carry that stored warmth across entire hemispheres. Without this oceanic heat transport, the tropics would be far hotter than they are, and the polar regions even colder. The ocean is Earth's great thermostat, and currents are the mechanism by which it keeps our planet's temperature in balance. Humans have known about and used these currents for as long as we've ventured onto the open ocean. Sailors have used major currents for faster navigation since ancient times. Polynesian navigators crossed vast stretches of the Pacific, using their knowledge of currents and swells to find islands separated by thousands of miles of open water. Spanish treasure fleets used the Gulf Stream to speed their journey home from the Americas. Even today, with all our modern navigation technology, shipping routes still take advantage of favorable currents to save fuel and time. The ocean offers these highways freely to those who understand them, just as it has for countless generations. The complexity of ocean currents reveals itself further when we look beneath the surface. The Ekman spiral causes deeper water to flow at angles to surface currents, creating a three-dimensional flow that's invisible from above. Named after the Swedish scientist who first described it, this phenomenon occurs because each layer of water is dragged along by the layer above it, but also deflected by the Coriolis effect. The result is that water at depth flows at an angle to the wind direction, with each successive layer flowing at a greater angle until, at a certain depth, water might actually be flowing in the opposite direction to the surface current above. It's a spiral of motion, turning through the depths, adding yet another layer of intricacy to the ocean's movements. All of this movement, all of these currents flowing ceaselessly across the globe, serve a purpose beyond just transporting heat and water. Currents distribute nutrients that support plankton blooms at the base of the food chain, making possible all the abundant life we associate with the sea. Microscopic plankton need sunlight and nutrients to grow, and currents bring those nutrients up from the depths and distribute them across vast areas of ocean. Where currents converge or where upwelling occurs, plankton populations explode, turning the water cloudy with life. These tiny organisms form the foundation of the entire marine food web. Small fish eat the plankton, larger fish eat the smaller fish, and so on up the chain to the great whales and sharks. Without currents to distribute nutrients, the ocean would be largely barren, a vast blue desert with life clinging only to the shallow margins. Instead, thanks to these rivers in the sea, the ocean teems with life from surface to floor, from pole to pole, in an abundance that has sustained humanity for millennia and continues to inspire wonder in all who contemplate the deep. Beneath the surface of our vast oceans, there exists a phenomenon so powerful and so constant that it shapes the very climate of our planet. Ocean currents act like giant rivers within the oceans, moving vast amounts of water globally, in patterns that have persisted for millennia. These underwater highways carry water across entire ocean basins, connecting distant shores in ways that might surprise you. Imagine a river, but one that flows through the sea itself, carrying with it warmth, nutrients, and the very essence of life across thousands upon thousands of miles. One of the most remarkable of these oceanic rivers is the Gulf Stream, a current so powerful that it can reach speeds of up to 2 meters per second. To put that in perspective, that's faster than many people walk, and we're talking about an incomprehensibly vast body of water moving at that pace. The Gulf Stream alone transports more water than all the rivers on Earth combined, flowing from the Gulf of Mexico up along the eastern coast of North America before turning eastward across the Atlantic. Its power is both gentle and immense, a paradox of nature that continues day and night, year after year, century after century. The mechanisms that drive these surface currents are elegant in their complexity. They're driven mainly by wind and Earth's rotation through something called the Coriolis effect. The wind pushes against the ocean surface, friction between air and water setting the uppermost layers in motion. But it's not quite that simple. As our planet spins on its axis, this rotation deflects moving objects, including water, to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection, the Coriolis effect, means that currents don't simply flow in the direction the wind pushes them. Instead, they curve and spiral, creating the great circular patterns we call gyres that dominate the surface of our oceans. These currents don't just move water, they move warmth itself. Warm currents transport heat from the equator toward the poles, moderating regional climates in ways that make certain places habitable that otherwise wouldn't be. The British Isles, for instance, sit at the same latitude as frigid Labrador in Canada, yet enjoy relatively mild winters. Why? The Gulf Stream and its extension, the North Atlantic Drift, carry tropical warmth northward, blessing these islands with temperatures far kinder than their latitude would suggest. Without these warm currents, much of northwestern Europe would be locked in ice for months each year. The ocean, in its generosity, redistributes the sun's warmth, creating temperate zones where life can flourish. But warmth isn't the only gift that currents carry. Cold currents bring nutrient-rich waters that enhance marine life and fisheries, creating some of the most productive ecosystems on Earth. When cold water rises from the depths, a process called upwelling, it brings with it nutrients that have settled to the ocean floor. These nutrients, phosphates and nitrates and other compounds essential for growth, fuel explosions of life near the surface. The cold Humboldt Current off the coast of Peru, for example, supports one of the world's most productive fishing grounds. The California Current does the same along the western coast of North America. These cold waters may not be comfortable for swimming, but they're brimming with the building blocks of life. All of these currents, both warm and cold, surface and deep, are connected in a vast system known as the Global Conveyor Belt. This planetary circulation connects surface and deep currents worldwide in a pattern that takes roughly 1,000 years to complete one full cycle. Warm surface water flows toward the poles, where it cools, becomes denser, and sinks into the deep ocean. This cold, dense water then flows back toward the equator at depth, eventually rising again to the surface to begin the journey anew. It's a circuit of almost unimaginable scale, linking every ocean basin, every sea, in a single interconnected system of perpetual motion. The amount of heat that these currents transport is staggering. Ocean currents transport far more heat than the atmosphere itself. While we often think of wind and air temperature when we consider climate, it's actually the ocean doing most of the heavy lifting when it comes to moving warmth around the planet. The ocean has a much greater capacity to hold heat than air does, and these currents carry that stored warmth across entire hemispheres. Without this oceanic heat transport, the tropics would be far hotter than they are, and the polar regions even colder. The ocean is Earth's great thermostat, and currents are the mechanism by which it keeps our planet's temperature in balance. Humans have known about and used these currents for as long as we've ventured onto the open ocean. Sailors have used major currents for faster navigation since ancient times. Polynesian navigators crossed vast stretches of the Pacific, using their knowledge of currents and swells to find islands separated by thousands of miles of open water. Spanish treasure fleets used the Gulf Stream to speed their journey home from the Americas. Even today, with all our modern navigation technology, shipping routes still take advantage of favorable currents to save fuel and time. The ocean offers these highways freely to those who understand them, just as it has for countless generations. The complexity of ocean currents reveals itself further when we look beneath the surface. The Ekman spiral causes deeper water to flow at angles to surface currents, creating a three-dimensional flow that's invisible from above. Named after the Swedish scientist who first described it, this phenomenon occurs because each layer of water is dragged along by the layer above it, but also deflected by the Coriolis effect. The result is that water at depth flows at an angle to the wind direction, with each successive layer flowing at a greater angle until, at a certain depth, water might actually be flowing in the opposite direction to the surface current above. It's a spiral of motion, turning through the depths, adding yet another layer of intricacy to the ocean's movements. All of this movement, all of these currents flowing ceaselessly across the globe, serve a purpose beyond just transporting heat and water. Currents distribute nutrients that support plankton blooms at the base of the food chain, making possible all the abundant life we associate with the sea. Microscopic plankton need sunlight and nutrients to grow, and currents bring those nutrients up from the depths and distribute them across vast areas of ocean. Where currents converge or where upwelling occurs, plankton populations explode, turning the water cloudy with life. These tiny organisms form the foundation of the entire marine food web. Small fish eat the plankton, larger fish eat the smaller fish, and so on up the chain to the great whales and sharks. Without currents to distribute nutrients, the ocean would be largely barren, a vast blue desert with life clinging only to the shallow margins. Instead, thanks to these rivers in the sea, the ocean teems with life from surface to floor, from pole to pole, in an abundance that has sustained humanity for millennia and continues to inspire wonder in all who contemplate the deep. The ocean is never truly still. Even in places where the surface appears calm, water is moving, shifting, responding to forces both visible and invisible. Near the shores where land meets sea, another force joins the great dance of ocean movement. Tides generate strong tidal currents near coastlines, pulling water in and out with the rhythmic rise and fall that follows the moon's patient orbit. Twice each day, in most places, the tide comes in and goes out again, and with it moves tremendous volumes of water through narrow channels, around headlands, between islands. These tidal currents can be fierce, creating whirlpools and rapids in the sea itself, places where the ocean seems to boil and churn with an energy that feels almost alive. Coastal communities have learned to respect these tidal flows, timing their activities to the predictable pulse of the tide, knowing that to fight against such currents is often futile. The paths these currents take are not random. They're shaped by the same invisible force that guides the great oceanic rivers across thousands of miles. Currents deflect right in the northern hemisphere and left in the southern hemisphere, a consequence of living on a spinning sphere. This deflection creates patterns that mirror each other across the equator, like reflections in water. In the north, currents curve clockwise in the Great Basins, while in the south they spiral counterclockwise, each hemisphere turning in its own direction as the planet rotates beneath them. It's a beautiful symmetry, a balance written in water and motion, playing out across the entire globe. The effect is subtle at first, but over distances of hundreds or thousands of miles, this gentle deflection shapes the very structure of ocean circulation. Of all the currents that circle our planet, one stands apart in its raw power. The Antarctic Circumpolar Current is the strongest current on Earth, flowing unobstructed around the entire continent of Antarctica. With no land masses to block its path, this mighty current circles endlessly through the Southern Ocean, driven by the fierce winds that howl across those latitude sailors once called the Roaring Forties and the Furious Fifties. The volume of water it moves is almost incomprehensible, more than 100 times the flow of all the world's rivers combined. It acts as a barrier, isolating Antarctica in a ring of cold water, keeping the continent frozen and pristine, separated from the warmer waters to the north. Day and night, year after year, this current flows eastward, never resting, never stopping, a ring of moving water encircling the bottom of the world. While surface currents capture our attention with their speed and visibility, there's another world of movement happening in the depths below. Deep ocean currents move slowly, driven by temperature and salinity differences rather than by wind. This is the realm of thermohaline circulation, where cold, salty water sinks in the polar regions and begins a journey that might last 1,000 years. These deep currents creep along the ocean floor at a pace so slow it would be invisible to any observer, yet they're moving water on a scale that staggers the imagination. The water that sinks near Greenland might not surface again until it reaches the Indian Ocean or the Pacific, centuries later. It's a patient process, operating on geological timescales, connecting today with a distant future, mixing the waters of the deep with the waters of the surface in a cycle that has continued since the oceans first formed. The influence of these currents, both fast and slow, surface and deep, extends far beyond the ocean itself. Ocean currents influence weather patterns, storms, and rainfall across entire continents. When warm water pools in one region, it heats the air above it, creating areas of low pressure that can spawn storms. The moisture that evaporates from warm currents falls as rain thousands of miles away. El Niño and La Niña, those recurring climate patterns that shift weather across the Pacific and beyond, are fundamentally about changes in ocean currents and water temperature. A shift in current patterns can bring drought to one region and floods to another. Hurricanes and typhoons draw their energy from warm ocean waters, and the currents that distribute this warmth help determine where these great storms will form and how strong they'll become. The atmosphere and ocean are partners in an intricate dance, each influencing the other, with currents playing a crucial role in this exchange. Not everything that currents carry is natural or beneficial. Floating debris follows currents, forming massive garbage patches in the centers of the great ocean gyres. Plastic bottles, fishing nets, microplastics, all the detritus of human civilization that finds its way to the sea gets swept up in the currents and carried along their paths. Where currents converge in the calm centers of gyres, this debris accumulates, creating zones where plastic fragments outnumber plankton. The Great Pacific Garbage Patch is perhaps the most infamous of these, but it's not alone. Each major ocean basin has its own accumulation zone, a reminder that currents connect all parts of the ocean, and what we discard in one place may end up circling for decades in another. These garbage patches are diffuse, not solid islands of trash as sometimes imagined, but rather vast areas where plastic particles drift suspended just below the surface, a modern tragedy written in the same currents that have supported life for eons. Yet currents continue their ancient work of nurturing life, even as they carry our mistakes. Upwelling currents bring deep nutrients to the surface, creating rich fishing grounds that have fed humanity for thousands of years. Where deep water rises, whether from underwater topography forcing water upward or from winds pushing surface water offshore, nutrients that have settled into the depths return to the sunlit zone where life can use them. These upwelling zones are among the most productive ecosystems on Earth. The waters off Peru, California, West Africa, they're all places where upwelling creates abundance. The water is cold, yes, and often cloudy with plankton, but it's teeming with fish. Anchovies, sardines, and the larger predators that feed on them gather in these regions, drawn by the richness that upwelling provides. The nutrients rising from the deep are like fertilizer for the ocean, fueling growth at every level of the food chain. The largest patterns in ocean circulation are the great rotating systems that dominate each major basin. Currents form large gyres spanning entire ocean basins, vast circles of water turning slowly in the North and South Pacific, the North and South Atlantic, and the Indian Ocean. These gyres are immense, each 1,000s of miles across, taking years for water to complete one full rotation. They're driven by the combination of wind patterns and the Coriolis effect, creating stable circulation patterns that persist year after year. The centers of these gyres are relatively calm, while the strongest currents flow along their edges. The Gulf Stream forms the western edge of the North Atlantic gyre. The Kuroshio current does the same for the North Pacific. These boundary currents are the highways where water moves fastest, while the interior of each gyre turns more slowly, a massive wheel of water spinning in perpetual motion. As we descend deeper into the ocean, the influence of the wind that drives surface currents begins to fade. Current strength decreases with depth due to friction and reduced wind influence, until at a certain point the water below moves almost independently of the surface above. The energy imparted by wind at the surface is dissipated as it's transferred downward through friction between layers of water. By the time you reach a few hundred meters down, the direct effect of wind is negligible, and other forces take over. Temperature, salinity, and the pressure of water above become the dominant factors. The deep ocean has its own circulation, its own currents, moving to a different rhythm than the wind-driven surface. It's a layered ocean, with different worlds stacked one atop another, each with its own patterns of flow. Through all these mechanisms, from the fastest surface currents to the slowest deep flows, from tidal pulses near shore to the great gyres spanning ocean basins, a single purpose emerges. Currents regulate Earth's climate by redistributing heat globally, maintaining the balance that makes our planet habitable. Without ocean currents, the equator would be unbearably hot and the poles even colder than they are now. Life would cling to a narrow band of temperate latitudes, and much of the Earth would be uninhabitable. Instead, currents carry warmth toward the poles and cold toward the equator, smoothing out the extremes, creating the climate zones we know. They work constantly, tirelessly, moving heat on a planetary scale, keeping Earth's temperature within the range where life can flourish. It's a system of such elegance and importance that we're only beginning to fully appreciate it. These rivers in the sea that connect all parts of the ocean and all regions of the world in one interconnected, life-sustaining flow. To measure something as vast as an ocean current requires a unit of measurement equally grand. Ocean currents are measured in sverdrups, equal to 1 million cubic meters per second. Named after the Norwegian oceanographer Harald Sverdrup, this unit captures the almost incomprehensible scale of water movement in the sea. 1 sverdrup is roughly equivalent to the flow of all the world's rivers combined, and yet some ocean currents transport 50, 100, or even more sverdrups. When scientists speak of the Gulf Stream carrying 30 sverdrups or the Antarctic circumpolar current moving 130, they're describing flows so massive that they dwarf anything we experience on land. It's hard to visualize 1 million cubic meters of water, let alone 100 million moving past a single point every second. Yet this is the scale at which the ocean operates, moving water in quantities that seem to belong more to astronomy than to Earth. Within these vast flows, individual water molecules journey on paths of extraordinary length. A single water droplet can take about 1,000 years to complete global circulation, traveling from the surface to the depths and back again, crossing from one ocean basin to another, touching every sea on its long voyage. Imagine a droplet of water at the surface today. It might sink in the cold waters near Greenland, joining the deep currents that flow southward along the ocean floor. It travels slowly, so slowly, creeping along at depths where no light penetrates, where the temperature hovers just above freezing. Centuries pass as it moves southward, then eastward around Antarctica, then northward into the Indian Ocean or the Pacific. Eventually, perhaps off the coast of South America or in the northern Pacific, it rises again to the surface, brought up by upwelling, seeing sunlight again for the first time in a millennium. It's a journey beyond human timescales, a voyage that connects past and future in a single molecule's path through the sea. Not all currents flow through open ocean. Some run along coastlines, shaped by the contours of continents, and these coastal currents have played crucial roles in human history. The Agulhas current flows along Africa's east coast and challenged early sailors attempting to round the Cape of Good Hope. This powerful current rushes southward along the coast of Mozambique and South Africa, carrying warm water from the Indian Ocean toward the meeting of two oceans at Africa's southern tip. Sailors in the age of exploration learned to fear the Agulhas, especially when strong southerly winds opposed the current, creating waves that could tower over ships. These waves, formed when wind and current clash, have claimed vessels even in modern times. The Portuguese, Dutch, and British mariners who pioneered the route to the East Indies had to master the art of working with or around the Agulhas, learning when to stay close to shore and when to swing wide into the ocean to avoid its force. The current still flows as it always has, indifferent to the ships that navigate its waters, a river of warm water racing along the continent's edge. Ocean currents don't just affect human activities, they shape the lives and movements of countless marine species. Certain currents shape tuna migration and habitat zones, creating boundaries and highways in the open ocean. Tuna are among the most wide-ranging fish in the sea, swimming thousands of miles in their lifetimes, and their movements are intimately connected to current patterns. Warm water species like yellowfin and big-eye tuna follow warm currents, while bluefin tuna range across temperature gradients, but still orient their migrations around current systems. Where currents converge or create fronts between different water masses, tuna gather, hunting the smaller fish and squid that also congregate in these productive zones. Commercial fishing fleets have learned to look for these current boundaries, knowing that where the water changes, the tuna will be. The currents create invisible territories in the open ocean, defining where species can thrive and where they cannot, structuring the pelagic world in ways we're only beginning to fully understand. Not all currents are created equal. The currents along the western edges of ocean basins differ markedly from those along the eastern edges. Western boundary currents are faster, deeper, and narrower than eastern currents, a consequence of how the Earth's rotation interacts with ocean circulation. The Gulf Stream, the Kuroshio off Japan, the Brazil Current, the Agulhas, these western boundary currents are the racing rivers of the ocean, concentrated flows of immense power. They're typically only 100 kilometers wide or less, but they run deep and fast, moving water at speeds that create distinct boundaries visible even from space. Eastern boundary currents, like the California Current or the Canary Current, are broader, shallower, and slower. They meander more, lacking the intensity of their western counterparts. This asymmetry gives each ocean basin a distinctive character, with one side featuring a narrow jet of fast-moving water and the other a broad, gentle flow. It's another example of how the ocean's behavior emerges from the interplay of rotation, wind, and the geography of continents. Far to the north, where ice meets water, another set of currents plays a crucial role in global circulation. Arctic currents contribute to polar water circulation, connecting the Arctic Ocean with the Atlantic and Pacific and playing a vital role in the global climate system. The cold waters of the Arctic flow southward through passages like the Fram Strait between Greenland and Svalbard, carrying sea ice and frigid water into the North Atlantic. Meanwhile, relatively warm Atlantic water flows northward, bringing heat to the Arctic even as it cools. These exchanges are essential for maintaining the Arctic environment and for driving the deep water formation that powers the global conveyor belt. The Arctic currents are changing as the climate warms and sea ice diminishes, with consequences that ripple throughout the entire ocean system. The ice edge currents, the boundary currents circling the Arctic basin, the flows through narrow straits, all of these are part of the machinery that connects the polar regions to the rest of the world ocean. Currents serve as transportation networks not just for water and heat, but for life itself. Ocean currents disperse marine species during larval stages, carrying the offspring of stationary adults to new homes far from where they were spawned. Most marine creatures, even those that spend their adult lives anchored to rocks or crawling along the bottom, have a larval phase when they drift in the currents. Coral spawn release eggs and sperm into the water, and the resulting larvae drift for days or weeks before settling. Lobsters, crabs, sea urchins, countless species release larvae that become part of the plankton at the mercy of currents. These larvae can travel hundreds of miles, crossing deep channels, reaching distant islands, connecting populations that might seem isolated. Currents act as highways of colonization, allowing species to spread across the ocean, maintaining genetic connections between distant populations and enabling recovery when local populations are depleted. Without currents to disperse larvae, the ocean would be a more fragmented place, with isolated populations more vulnerable to extinction. The currents that have flowed in consistent patterns for millennia are now changing. Climate change is warming major currents faster than the global average, altering their speed, their paths, and their effects on regional climates. The Gulf Stream appears to be weakening, its flow less robust than in decades past. The warming waters of the Arctic are changing circulation patterns there. As ice melts, adding fresh water to the ocean, it affects salinity and density, the very properties that drive deep water formation. Some models suggest that key components of ocean circulation could slow significantly in coming decades, with profound consequences for climate. The currents that have regulated Earth's temperature for so long are themselves being affected by the warming they once balanced. It's a feedback loop, a system responding to change in ways that create more change, and scientists watch with concern as the patterns shift, knowing that small changes in ocean circulation can have outsized impacts on global climate. Deep below the surface, currents follow paths determined by the shape of the seafloor. Some deep currents follow continental slopes for thousands of kilometers, guided by underwater topography as rivers are guided by valleys. These deep boundary currents hug the edge of continents, flowing along the transition zone between shallow coastal waters and the abyssal depths beyond. They're invisible from above, unmarked by any surface disturbance, yet they transport vast amounts of water and heat. The deep western boundary current of the Atlantic, for instance, carries cold water southward from its formation regions near Greenland, following the continental slope of North America and then South America, all the way to the Southern Ocean. These currents are explored by robotic submarines and tracked by instruments anchored to the seafloor, revealing a hidden world of movement in the depths, currents that never see the sun yet play crucial roles in the ocean's grand circulation. As humanity searches for sustainable energy sources, attention has turned to the ceaseless motion of the sea. Ocean currents are being tested as renewable energy sources, with experimental turbines placed in strong tidal currents and boundary currents. The idea is simple in principle. Place a turbine in a flow of water, just as wind turbines are placed in flows of air, and extract energy from the moving water. The Gulf Stream off Florida, the Kuroshio off Japan, tidal passages around the British Isles, all are being studied as potential sites for current-generated power. The energy is there, constant and predictable, no storage needed as with solar, no dependence on weather as with wind. The challenges lie in engineering devices that can withstand the corrosive ocean environment, avoid harming marine life, and generate power economically. The atmosphere provides some of this heat transport through winds and weather systems, but the ocean does even more, carrying vast quantities of heat in its currents. Warm water flows poleward, releasing heat to the atmosphere as it goes, moderating temperatures thousands of miles from where the water was first warmed. Cold water flows equatorward, helping to cool the tropics. It's a heat engine operating on a planetary scale, powered by the sun, regulated by the ocean circulation, maintaining the balance that allows life to exist from pole to pole. Some currents have regional importance out of proportion to their size. The loop current circulates through the Gulf of Mexico, entering through the Yucatan Channel, swinging northward and eastward in a great loop, then exiting through the Straits of Florida where it becomes the Gulf Stream. This current brings warm Caribbean water into the Gulf, influencing the climate of the Gulf Coast, affecting the paths of hurricanes, and occasionally shedding large rings of warm water that drift westward across the basin. These loop current rings, some more than 100 miles across, are features unto themselves, moving independently, lasting for months, containing tropical water surrounded by the cooler waters of the Gulf. The loop current varies in its path and strength, sometimes extending far northward into the Gulf, other times staying closer to the southern rim. This variability affects everything from water temperature at beaches to nutrient distribution to the intensification of hurricanes that cross the current's warm water. In the cold currents that bring nutrient-rich water from the depths, the foundation of oceanic productivity is renewed continuously. Cold currents fuel plankton growth by supplying nitrogen and phosphates, the essential nutrients that limit biological production in much of the ocean. The surface waters, bathed in sunlight, have plenty of energy for photosynthesis, but without nutrients that sunlight goes largely unused. The cold water rising from depth or flowing from polar regions brings nitrogen compounds and phosphorus compounds that have accumulated in the deep, where organic matter settling from above has decomposed and released its constituent elements. When this nutrient-rich water reaches the sunlit surface, plankton populations explode, turning the water green with chlorophyll. These blooms support the entire food web, from tiny zooplankton to the great whales. The cold currents, uncomfortable as they make swimming, are the currents of abundance, the flows that feed the ocean's most productive fisheries and support the greatest concentrations of marine life. The warmth that moves through the ocean in currents doesn't just affect climate on a global scale, it shapes ecosystems at a local level as well. Regional warm currents shape local marine ecosystems, determining which species can survive in a given area and supporting communities of tropical or subtropical organisms far from the equator. Coral reefs exist in places they otherwise couldn't because warm currents bathe them year-round. Fish species extend their ranges along corridors of warm water. Kelp forests end where warm currents begin, unable to tolerate the heat. These warm currents create pockets of tropical conditions in temperate latitudes, allowing mangroves to grow in places that should be too cold, supporting seagrass meadows and coral communities at latitudes where their cousins in colder waters have long since given up. The currents essentially extend climate zones along their paths, carrying not just heat but the possibility of life, allowing organisms to thrive far from their ancestral homes. In the great sweep of currents around the planet, certain patterns emerge from the geography of continents and the physics of rotating fluids. Some currents flow west to east around southern continents, taking advantage of the openings between land masses at southern latitudes. The Antarctic circumpolar current is the prime example, but elements of westward to eastward flow appear in other southern regions as well, wherever ocean can flow relatively unimpeded by land. This west to east motion is favored in the southern hemisphere, where the spaces between continents are wider and fewer land masses block the path. In the northern hemisphere, by contrast, currents must navigate around and between continents, creating more complex patterns. The south has an openness that the north lacks, a geographical asymmetry that manifests in how water circulates. These west to east flows in the south help mix water between ocean basins, contributing to the global homogenization of deep waters and playing their part in the grand circulation that connects every part of the ocean in one vast, interconnected system of perpetual motion. Along the eastern coast of Florida, where the continent meets the Atlantic, a tremendous force of water flows northward with a power that defies easy comprehension. The Florida current transports tens of millions of cubic meters of water each second, a river in the ocean so vast that it dwarfs any flow on land. This is the beginning of the Gulf Stream, the point where the loop current from the Gulf of Mexico exits through the narrow straits of Florida and becomes one of the most studied currents in the world. The strait concentrates the flow, squeezing it between Florida and the Bahamas, accelerating it to speeds that make it visible from satellites, a distinct boundary between the deep blue of the stream and the lighter coastal waters to either side. Ships crossing from Miami to the Bahamas must account for this current, either working with it or fighting against it, depending on their direction. Tens of millions of cubic meters every second, hour after hour, day after day, an unceasing flow that has run for thousands of years and will continue for thousands more, carrying tropical warmth northward along the coast. When we look at the ocean from above, from the perspective of satellites or global maps, patterns emerge that reveal the fundamental structure of ocean circulation. 5 major subtropical gyres dominate global ocean circulation, great wheels of water turning in the North and South Atlantic, the North and South Pacific, and the Indian Ocean. These gyres are persistent features, stable patterns that have existed for as long as the continents have held their current positions. Each gyre spans thousands of miles, its edges marked by the strongest currents, its center relatively calm. The gyres turn clockwise in the northern hemisphere and counterclockwise in the southern, driven by trade winds and westerlies, shaped by the Coriolis effect, bounded by continents. They organize the flow of the ocean, creating predictable patterns that sailors have used for centuries and that continue to structure how heat and nutrients and life itself are distributed across the ocean basins. Within these gyres, water slowly spirals, taking years to complete one rotation, while along their edges the boundary currents race at speeds that make them the highways of the sea. Not all water masses are created equal. Some have properties that make them particularly important in the ocean's circulation. Subantarctic mode water forms near Antarctica and spreads northward, a distinct layer of water with uniform temperature and salinity that forms during the southern winter. When storms rage in the Southern Ocean, cooling and mixing the surface waters, this mode water is created, a thick layer that then spreads beneath the surface as it moves northward, carrying oxygen and nutrients into the interior of the ocean. It's called mode water because of its uniform properties, a homogeneous layer that can be hundreds of meters thick, sliding between the warmer waters above and the colder deep waters below. This water mass plays a crucial role in the ocean's ability to absorb carbon dioxide from the atmosphere and in supplying oxygen to deeper layers where marine life depends on it. The subantarctic mode water is one of several mode waters found in different parts of the ocean, each contributing to the three-dimensional circulation that makes the ocean so much more than a simple surface flow. Far to the north, where the Atlantic meets the Arctic, currents carry consequences beyond their immediate transport of water. Northern Atlantic currents influence Arctic ice melt, bringing relatively warm water into the Arctic Ocean, where it circulates beneath the ice, delivering heat that contributes to melting from below. The West Spitsbergen Current, an extension of the Gulf Stream system, carries Atlantic water northward past Norway and Svalbard, entering the Arctic basin where it sinks beneath the fresher, colder surface layer. This Atlantic water, though cooled during its journey north, is still warmer than the water that formed in the Arctic itself, and its heat affects sea ice extent and thickness. As the climate warms, these currents are changing, potentially bringing even more heat to the Arctic, accelerating the loss of sea ice that has proceeded at an alarming rate over recent decades. The currents link the tropical Atlantic with the Arctic ice cap, demonstrating once again how the ocean connects distant regions in chains of cause and effect that span the globe. Currents don't just move water and heat, they move gases essential for life. Ocean currents mix oxygen and carbon dioxide across vast areas, distributing these gases from regions where they enter the ocean to regions where organisms need them. Oxygen enters the ocean at the surface, where waves and wind mix air and water, but marine life exists at all depths, and many organisms live far from the surface where oxygen is replenished. Currents carry oxygen-rich water from the surface to the depths, allowing life to exist in the dark interior of the ocean. Similarly, carbon dioxide dissolves in cold surface waters and is carried downward and around the ocean by currents, removing it from the atmosphere and storing it in the deep sea. This oceanic uptake of carbon dioxide has slowed the pace of climate change, with the ocean absorbing a significant fraction of the CO2 that human activities have released. The currents make this possible, creating a circulation that brings surface water into contact with the atmosphere and then moves it into the interior, where the gases it carries can remain for centuries before returning to the surface. The heat that currents carry shapes the climates of the lands they pass. Warm currents moderate polar climates in northern regions, making places habitable that would otherwise be locked in ice. Norway, Iceland, the northern British Isles, all benefit from the warmth brought by the Gulf Stream's extension into the Norwegian Sea and beyond. These regions lie at latitudes comparable to Alaska or northern Canada, yet their climates are far milder. Ice-free ports at latitudes where pack ice should prevail, green landscapes where tundra might be expected, all thanks to the ocean currents delivering tropical heat to polar latitudes. The effect is so pronounced that Hammerfest, Norway, one of the northernmost towns in the world, has milder winter temperatures than places in Alaska 1,000 miles farther south. The ocean gives freely of the heat it has transported across thousands of miles, moderating the extremes that latitude alone would dictate, creating climate anomalies that have allowed civilizations to flourish in far northern lands. The ocean is turbulent, and from this turbulence emerge features that, while temporary, can be significant in their own right. Massive ocean eddies can trap marine life and pollutants, creating isolated pockets of water that rotate and drift through the ocean for months. Early installations have shown promise, and as the technology develops, ocean currents might one day contribute significantly to our energy needs, finally harnessing in a practical way the tremendous power that has flowed through the sea since the world was young, turning the eternal movement of the ocean into light and warmth for human homes. The ocean has layers, not just of temperature and light, but of movement itself. While waves and surface currents capture our attention from above, another realm of flow exists in the darkness below. Deep currents transport water between continents beneath the surface, carrying cold, dense water along pathways that span entire ocean basins. These are the return flows of the Great Conveyor Belt, the water that sank in polar regions now making its way slowly back toward the equator along the ocean floor. This deep water travels beneath the surface currents, completely independent, moving in different directions, at different speeds, sometimes even flowing opposite to the currents above. A ship sailing east on the surface might be passing over water flowing west at depth, two rivers occupying the same space but separated by pressure and density. These deep currents connect the Atlantic with the Pacific, the Indian Ocean with the Southern Ocean, all beneath the surface, invisible yet integral to how the ocean functions as a whole. The ocean is not static, and neither are the forces that drive it. As our planet warms, the patterns of flow are shifting in response. Surface warming has accelerated upper ocean currents across most of the planet, with measurements showing that the speed of major currents has increased over recent decades. Warmer water holds more energy, and this additional energy translates into motion. The atmosphere is warming, the winds are changing, and the currents respond, flowing faster through their ancient channels. This acceleration has implications for how heat is distributed, how nutrients are transported, how marine species move through the ocean. It's another way that climate change manifests in the ocean, not just through rising temperatures but through the quickening pulse of circulation itself. The currents are speeding up, carrying their cargo of heat and life at a pace unprecedented in recent history, and scientists work to understand what this acceleration might mean for the future of ocean ecosystems and global climate alike. One current stands apart in its role as connector and barrier both. The Antarctic Circumpolar Current links all ocean basins together, serving as the one place where water from the Atlantic, Pacific, and Indian Oceans all mix. Flowing unobstructed around Antarctica, this current acts as a great mixing zone, stirring together waters from 3 oceans in its endless eastward flow. It's the only current that circumnavigates the globe, never meeting land, forever circling the frozen continent at the bottom of the world. In this mixing, the distinctions between ocean basins blur. Water that left the Atlantic years ago becomes indistinguishable from Pacific water, both swirling together in the cold Southern Ocean. Yet even as it mixes, the Antarctic Circumpolar Current also isolates, creating a thermal boundary that keeps Antarctica cold. It's a paradox of connection and separation, linking all oceans while simultaneously protecting the Antarctic ecosystem from warmer waters to the north. Near coastlines, in bays and straits, tidal currents dominate the rhythm of water movement, but they don't flow in isolation. Tidal currents are influenced by wind, seafloor shape, and air pressure, factors that can amplify or diminish the tidal flow. A strong wind blowing with an outgoing tide will drain a bay more quickly, exposing tidal flats that might otherwise remain submerged. The shape of the seafloor funnels tidal currents, concentrating their force in narrow passages, creating the fierce tidal races that mariners navigate with care. Even atmospheric pressure plays a role. High pressure pushing down on the ocean surface, low pressure allowing it to rise, adding or subtracting inches or even feet to the predicted tide. These factors combine in complex ways, making tidal prediction an art as much as a science, especially in complicated coastlines with multiple channels and varying depths. The tide rises and falls with astronomical precision, but the currents that accompany it respond to immediate local conditions, creating flows that vary from day to day, from hour to hour. Major currents don't always flow as single, unified streams. Often they split and divide, sending branches in different directions. Branching currents affect regional circulation patterns, creating smaller-scale gyres and eddies that influence local conditions. The Gulf Stream, for instance, sheds rings and meanders that can separate and travel independently, carrying warm water into regions usually dominated by cold, or vice versa. The Kuroshio has extensions that branch northward and eastward into the North Pacific. These branches are not random. They form in response to bottom topography, wind patterns, and the interactions between different water masses. Each branch carries with it heat, nutrients, and organisms, distributing them across regions that the main current doesn't directly reach. The branching creates complexity in ocean circulation, turning simple diagrams into intricate webs of flow, with multiple pathways connecting different parts of the ocean. All of this circulation, from the great boundary currents to the smallest branch flow, serves a fundamental purpose in Earth's climate system. Ocean currents redistribute solar energy from equatorial to polar regions, counteracting the imbalance in heating that would otherwise make the planet uninhabitable. The equator receives more solar energy than it can radiate back to space, while the poles receive less than they lose. Without some mechanism to move heat poleward, the tropics would grow ever hotter and the poles ever colder until the difference became extreme. These eddies spin off from major currents, rings of water that separate and become independent features, some rotating clockwise, others counterclockwise, depending on whether they're warm core or cold core eddies. Inside an eddy, water circulates in its own closed loop, isolated from the surrounding ocean. Fish and plankton can become trapped in these rotating systems, carried far from their usual habitats. Pollutants and nutrients are also confined, creating localized regions of unusual chemistry or productivity as the eddy drifts. Some eddies are 100 miles across, large enough to affect local weather, substantial enough to alter ship routes. They drift slowly, following the larger currents, sometimes lasting 6 months or more before finally mixing back into the surrounding ocean and disappearing. Beneath the surface currents that flow generally westward along the equator, a surprise awaits. The equatorial undercurrent flows eastward beneath surface waters, a ribbon of swift flow running in the opposite direction from the currents above. This undercurrent sits 100 or more meters below the surface, hidden from view but detectable by instruments lowered from ships or by autonomous floats drifting at depth. It forms as a result of pressure gradients set up by the westward flowing surface currents, essentially a return flow compensating for the water piled up in the western Pacific by the trade wind-driven currents above. The equatorial undercurrent is remarkably consistent, a persistent feature that flows year-round, carrying water and nutrients eastward across the Pacific and Atlantic. Its discovery was a surprise to oceanographers, revealing that even in regions where surface flow seemed straightforward, the ocean held hidden complexity, currents within currents, flows stacked one atop another in an intricate vertical structure. In the deep waters surrounding Antarctica, ancient processes are occurring that have implications for the entire planet. Deep waters near Antarctica release ancient stored carbon dioxide, water that sank centuries or millennia ago carrying dissolved CO2 now returning to the surface. When this water rises through upwelling, its carbon dioxide is released to the atmosphere, a natural part of the ocean's carbon cycle. For most of human history, this release was balanced by uptake elsewhere, a steady-state exchange between ocean and air. But now, as the ocean warms and circulation patterns change, questions arise about whether this balance will hold. The Southern Ocean is a critical region for carbon cycling, and the waters rising around Antarctica represent one of the major pathways by which carbon stored in the deep ocean returns to active circulation. The fate of this carbon, whether it remains in the ocean, returns to the atmosphere, or is taken up by phytoplankton blooms around Antarctica, is a question with major implications for future climate. At the top of the world, circular currents trap more than just water. Arctic gyres trap fresh water and influence sea ice stability, creating regions where low salinity water accumulates beneath the ice. The Beaufort Gyre, the largest of these Arctic circulation patterns, has been accumulating fresh water for years, a reservoir of low salinity water trapped in its circulation. This fresh water comes from river runoff, ice melt, and relatively fresh water from the Pacific flowing through the Bering Strait. The gyre holds this fresh water, preventing it from mixing with the saltier Atlantic water below. This stratification has profound effects on sea ice, as the fresh water at the surface freezes more easily and insulates the warmer water below. If the gyre's circulation weakens or reverses, this accumulated fresh water could be released, potentially affecting ocean circulation in the North Atlantic thousands of miles away. The Arctic gyres are thus reservoirs and gatekeepers both, holding fresh water in temporary storage while the ice above grows and melts with the seasons, part of the complex machinery of polar circulation that links ice, ocean, and atmosphere in feedbacks we are only beginning to fully understand. At the boundary between sea and sky, where waves rise and fall and wind stirs the surface into motion, an exchange is constantly taking place. Wind-driven surface cells enhance gas exchange between ocean and atmosphere, mixing the upper layers of water so thoroughly that gases can move freely between air and sea. When wind creates waves and churns the surface, it doesn't just move water horizontally, it mixes it vertically, pulling deeper water toward the surface and pushing surface water downward. This mixing brings oxygen from the air into the ocean, replenishing what marine organisms consume, and it allows carbon dioxide dissolved in seawater to escape back to the atmosphere. The more vigorous the wind, the more complete the mixing, the faster the exchange. In storm-tossed seas, the entire upper layer of the ocean can be stirred into a froth, saturating with oxygen, equalizing its gas content with the air above. These wind-driven cells, spinning and mixing at scales from meters to kilometers, are essential to maintaining the chemical balance between ocean and atmosphere, keeping both systems connected in a continuous dialogue of exchange. For centuries, sailors knew the surface currents of the equatorial oceans, using the westward-flowing trade wind currents to cross from Africa to the Americas or from the Americas to Asia. But beneath these familiar flows, something unexpected was hiding. The equatorial undercurrent was formally identified in the mid-20th century, though hints of its existence had been noticed earlier. Scientists lowering instruments to measure current speed at depth found, to their surprise, that while surface water flowed westward as expected, water 100 meters down flowed strongly eastward. The discovery sparked renewed exploration of equatorial circulation, revealing that the simple picture of trade winds pushing water westward was incomplete. The undercurrent is now known to be a fundamental part of tropical ocean dynamics, a compensating flow that develops in response to the pressure gradients created by surface currents. Its discovery was a reminder that the ocean still held surprises, that even in well-traveled waters, the depths could conceal flows unknown to earlier generations. The forces that shape ocean currents are not only wind and density, but also the subtle balance between pressure and the planet's rotation. Geostrophic currents balance pressure and rotational forces, flowing not directly from high pressure to low pressure as you might expect, but at right angles to the pressure gradient, parallel to lines of equal pressure. This seems counterintuitive until you remember that everything moving on Earth's surface is subject to the Coriolis effect, that apparent deflection caused by the planet's rotation. In the ocean, pressure differences created by piled-up water are balanced by the Coriolis force, resulting in currents that flow along the slope of the sea surface rather than down it. Most of the major permanent currents away from the equator are geostrophic, existing in this balance between opposing forces. It's a delicate equilibrium, persistent and stable, allowing currents to flow for thousands of miles without the continuous input of wind energy once they're established. The mathematics of geostrophy underlies much of our understanding of ocean circulation, describing how pressure and rotation together determine the paths that water takes through the sea. Not all currents are constant in direction. In some regions, the currents themselves change with the seasons, reversing their flow entirely. Some currents reverse direction seasonally due to monsoon winds, particularly in the Indian Ocean where the monsoon system is most pronounced. During the summer monsoon, winds blow strongly from the southwest across the Indian Ocean, driving currents in one direction. When winter comes and the monsoon reverses, winds blow from the northeast and the currents reverse too, flowing back the way they came. The Somali current off the coast of East Africa is perhaps the most dramatic example, becoming one of the strongest currents in the world during the summer monsoon, only to reverse and flow southward when winter arrives. This seasonal reversal affects everything from fishing to navigation to nutrient distribution, creating environments that change profoundly twice a year. It's a reminder that the ocean responds to the atmosphere, that wind patterns dictate current patterns, and that in some places this relationship plays out in dramatic seasonal reversals. In the deepest parts of the ocean, in the trenches and basins where sunlight has never penetrated and where pressure would crush any surface-dwelling organism, a particular water mass has found its home. Antarctic bottom water fills the deepest ocean trenches, the coldest, densest water in the world spreading along the seafloor from its formation site around Antarctica. This water forms when surface water near the Antarctic coast is cooled to temperatures below freezing, becoming so dense that it sinks all the way to the bottom. From there it spreads outward, flowing slowly northward along the abyssal plains, filling the deepest parts of the Atlantic, Pacific, and Indian Oceans. It moves at a glacial pace, taking centuries to cross an ocean basin, but its influence is global. This is the end point of the conveyor belt sinking branch, the water that has released all its heat, given up all its oxygen to the deep, and now creeps along the bottom until eventually, somewhere far away, it will begin its slow rise back toward the surface. The Antarctic bottom water represents the deep memory of the ocean, water that last saw daylight generations ago, now residing in eternal cold and darkness at the bottom of the world. Not far behind in the depths flows another major water mass, formed in a different polar region. North Atlantic deep water sinks near Greenland and flows southward, traveling along the western edge of the Atlantic basin at depths of 1 to 3 kilometers. This water forms when the Gulf Stream's warm water reaches the cold northern Atlantic, where it loses its heat to the atmosphere, becomes dense, and sinks. The sinking occurs primarily in the Labrador Sea and in the waters between Greenland and Scandinavia, regions where winter cooling is intense and where the conditions are just right for deep water formation. Once formed, this water mass flows southward as a deep current, beneath the Gulf Stream that flows northward at the surface, an elegant counter-circulation connecting surface and deep ocean. The North Atlantic deep water spreads throughout the Atlantic and eventually into the other ocean basins, carrying oxygen and nutrients into the depths, ventilating the deep ocean and maintaining conditions that allow life to exist even thousands of meters below the surface. The currents that we've been exploring don't just carry water and heat and dissolved gases, they also carry life itself in its most vulnerable stages. Currents transport larvae across thousands of kilometers, connecting distant populations of marine organisms in ways that would be impossible for the adults. A coral spawn released on one reef might drift in the currents for weeks before finally settling on a reef hundreds or even thousands of kilometers away. Fish larvae, too small to swim against any current, go where the water takes them, sometimes traveling vast distances before metamorphosing into juveniles and beginning their independent lives. This larval dispersal is critical for maintaining genetic diversity, for allowing species to colonize new habitats, and for enabling populations to recover from local extinctions. The currents are inadvertent carriers, transport systems that move billions of tiny organisms each year, connecting the ocean's ecosystems in networks of relationship and exchange. A single strong current event can seed a distant ecosystem with the offspring of creatures from far away, and over time these connections accumulate, creating biogeographic patterns that reflect the structure of ocean circulation. The ocean's vertical structure continues to surprise us with its complexity. We've spoken of the equatorial undercurrent flowing east beneath westward surface flow, but this pattern of opposition appears elsewhere too. Undercurrents can flow opposite to surface currents in many regions, particularly along coasts where wind-driven surface flow is strong. These undercurrents are compensating flows, water moving beneath the surface to balance the water being pushed along at the top. Along the coast of California, for instance, When strong northwesterly winds drive surface water offshore, deeper water flows southward and onshore to replace it. The result is often a two-layer flow, surface water moving one way, subsurface water moving another. Fishermen and sailors who understand these patterns can use them to their advantage, finding favorable currents at different depths, but they also create hazards, unexpected flows that can catch the unwary by surprise. These opposing flows at different depths are yet another example of how the ocean operates in three dimensions, with different layers moving independently, each responding to different forces. When oceanographers study the ocean's energy budget, trying to understand where energy enters the system and how it's distributed, they found something remarkable. Mesoscale eddies account for a large share of ocean energy, these swirling features containing more kinetic energy than the mean currents themselves. The eddies are constantly being created and destroyed, spinning off from major currents, drifting across ocean basins, eventually dissipating their energy through friction and mixing. Despite being temporary features, their collective impact is enormous. They transport heat and salt laterally, mixing water properties across the ocean. They trap and transport organisms and nutrients. They interact with the atmosphere, affecting weather. The ocean, it turns out, is not primarily a system of steady currents but rather a turbulent field of eddies through which the mean currents thread their way. This was a discovery that came from satellite observations, which revealed the ocean surface to be constantly rippling with these mesoscale features, swirls and rings and meanders decorating the surface like weather systems in the atmosphere, each one a temporary but significant feature in the ocean's continuous motion. The major currents we've discussed, the Gulf Stream and Kuroshio and Antarctic Circumpolar Current, are the main highways of the ocean, but they send out branches that can be equally important at smaller scales. Branch currents influence isolated marine ecosystems, carrying water and the organisms it contains to places that wouldn't otherwise receive them. A branch current might split from a major flow and curve into a bay or around an island, bringing warm water to a cold coast or cold water to a warm one, creating local conditions that support unique communities of marine life. These branches can be seasonal or permanent, strong or weak, but wherever they go, they carry with them the signature of their parent current. Islands in the path of warm branches might host coral reefs at latitudes where corals couldn't otherwise survive. Cold branches might bring nutrient-rich water to otherwise unproductive coasts, creating local hotspots of marine life. The branching of currents creates diversity in the ocean, breaking up what might otherwise be homogeneous regions into a mosaic of different conditions, each supporting its own characteristic suite of species, all connected by the flowing water that links them together. To truly grasp the power of ocean currents, we need to think in terms that stretch the imagination. The Gulf Stream carries water volumes comparable to thousands of waterfalls per second, a flow so immense that all comparisons seem inadequate. Picture Niagara Falls, with its thundering cascade that draws millions of visitors each year to witness its power. Now multiply that by 1,000, and you begin to approach the volume of water that the Gulf Stream moves past any given point each second. It's a ceaseless torrent, wider than many countries, deeper than most mountains are tall, flowing day and night without pause. This tremendous flux of water carries with it heat equivalent to millions of power plants, warmth drawn from the tropical Atlantic and delivered northward to moderate the climate of an entire hemisphere. The Gulf Stream is not just a current, it's a fundamental feature of Earth's climate system, a river in the ocean so vast that its influence reaches far inland, shaping weather patterns and temperature across continents. The speed at which these great currents flow can rival that of rivers on land, though we rarely think of ocean water as moving quickly. Major ocean currents can move as fast as 5 miles per hour, swift enough that a floating object would cover more than 100 miles in a day. The Gulf Stream at its fastest points reaches these speeds, as does the Agulhas current off Africa's coast. 5 miles per hour might not sound impressive compared to a car or even a bicycle, but for water, for the ocean itself to be moving that quickly over such vast areas and depths, represents an enormous transfer of momentum and energy. Ships traveling against such currents find their progress slowed significantly, while those traveling with the current receive a free boost, saving fuel and time. For sailors in the age before engines, understanding where these fast-flowing currents ran and how to use them was the difference between a successful voyage and disaster, between arriving with provisions to spare or running out of food and water far from any shore. The knowledge of ocean currents that we now take for granted had to be discovered and mapped through careful observation. Benjamin Franklin produced one of the first current maps, documenting the Gulf Stream's path based on information from whaling captains and his own temperature measurements taken during Atlantic crossings. Franklin realized that mail ships sailing from England to America were taking significantly longer than merchant ships making the same voyage, and he suspected the Gulf Stream was to blame. The mail ships, following a more northerly route, were fighting against the current for much of their journey, while the merchant vessels took a more southerly route that avoided the strongest flow. Franklin's map, published in the late 18th century, showed the Gulf Stream as a distinct feature with defined edges and a clear path northward along the American coast before curving eastward across the Atlantic. It was one of the first attempts to systematically document ocean circulation, and it demonstrated that careful observation and indigenous knowledge, in this case from experienced mariners, could reveal the ocean's hidden structure. On the other side of the Pacific, another great current shapes the environment and economy of an island nation. The Kuroshio Current is vital to Japan's climate and fisheries, bringing warm tropical water northward along Japan's eastern coast. The name Kuroshio means black current in Japanese, referring to the deep blue color of its warm, clear water, so different from the greenish coastal waters through which it flows. The warmth that the Kuroshio brings moderates Japan's climate, keeping ports ice-free in winter, allowing a temperate climate to extend farther north than it otherwise would. The current also brings nutrients and organisms, supporting productive fishing grounds where warm water and cold water species mix. Tuna follow the Kuroshio on their migrations, and fishermen have learned to work its edges where different water masses meet and fish congregate. Like the Gulf Stream in the Atlantic, the Kuroshio is more than just a current. It's a defining feature of the ocean basin it inhabits, influencing everything from weather to wildlife to human settlement patterns along thousands of miles of coastline. While warm currents capture attention for the climate moderation they provide, cold currents have their own crucial roles to play. Cold eastern boundary currents support major fishing industries, their cool, nutrient-rich waters creating some of the most productive marine ecosystems on the planet. The California Current along North America's west coast, the Canary Current off northwest Africa, the Peru or Humboldt Current along South America's west coast, the Bengala Current off southwest Africa, these eastern boundary currents are the breadbaskets of the ocean. They flow slowly compared to their western counterparts, but they're associated with upwelling, the rise of deep water to the surface that brings nutrients into the sunlit zone where phytoplankton can use them. The resulting blooms of microscopic life support vast populations of small fish like anchovies and sardines, which in turn support larger predators and seabirds. These regions may account for a tiny fraction of the ocean's total area, yet they produce a disproportionate share of the world's fish catch, testament to the productivity that cold, nutrient-rich currents can generate. The great currents of the ocean don't flow in straight lines across featureless plains. They encounter obstacles, and their responses to these barriers create complexity in circulation patterns. Equatorial currents split around islands and land barriers, dividing and then rejoining, creating eddies and countercurrents in the lee of obstacles. When the North Equatorial Current encounters an island chain like the Philippines or Indonesia, it must split, some water flowing north of the islands, some south, before the two branches rejoin on the far side. These splits create regional circulation patterns, gyres within gyres, that can trap water and create distinct ecosystems around islands. The Galapagos Islands sit at the confluence of multiple currents, creating the unique oceanographic conditions that support their remarkable endemic species. Australia splits the South Equatorial Current, creating different circulation patterns in the Pacific and Indian Oceans. Every island, every peninsula, every continental margin modifies the flow around it, and the ocean circulation becomes a complex tapestry woven from countless interactions between water and land. Along South America's west coast, a cold current does more than just cool the water. The Humboldt Current cools air and contributes to desert formation, creating the hyper-arid Atacama Desert, one of the driest places on Earth. The mechanism is elegant in its simplicity but profound in its effects. The cold current cools the air above it, and cold air holds less moisture than warm air. As this cooled air moves onshore, it's warmed by contact with the land, but instead of releasing moisture as rain, warm air over land draws moisture up from the soil and vegetation, drying the landscape even further. Additionally, the cooled air creates a stable atmospheric layer that prevents clouds from rising and producing rain. The result is that even though the Atacama lies right next to the ocean, source of all moisture, it receives almost no rainfall. Some weather stations in the Atacama have never recorded measurable precipitation. The cold current, rather than bringing the gift of moisture, creates a rain shadow along the coast, a band of desert that extends for thousands of miles, interrupted only where geography allows moist air to penetrate from other directions. The major gyres that dominate each ocean basin create strong, consistent flows in predictable directions, but the ocean is not content with simple patterns. Countercurrents flow opposite to dominant gyres, creating return flows that balance the gyre circulation. Between the North and South Equatorial Currents in both the Pacific and Atlantic, the equatorial countercurrent flows eastward, returning water that the trade wind-driven currents have pushed westward. Along coastlines, countercurrents sometimes flow opposite to the main boundary current, creating complex patterns of circulation. These countercurrents are essential for maintaining balance in the ocean, preventing water from piling up endlessly in one region. They're often deeper or narrower than the main currents, sometimes harder to detect, but they're always there, providing the return path that allows circulation to continue. The ocean is a closed system, and for every flow in one direction, there must be a compensating flow in the opposite direction, whether at the surface or in the depths, creating the balanced circulation that characterizes ocean dynamics. Off the southwestern coast of Africa, cold water wells up from the depths, creating conditions that mirror those of the other great eastern boundary current systems. The Bengala Current creates one of the world's richest fishing zones, its cold, nutrient-laden waters supporting enormous populations of fish. Sardines and anchovies swarm in massive schools, and following them come the predators. Larger fish, Cape fur seals, seabirds in flocks so large they darken the sky. The Bengala upwelling system is particularly intense where southeasterly winds blow parallel to the coast, pushing surface water offshore and causing deeper water to rise to replace it. This upwelled water is rich in nitrates and phosphates, the nutrients that limit biological production in most of the ocean. When they reach the sunlit surface waters, phytoplankton populations explode, turning the water green and setting off a chain reaction of growth at every level of the food web. The fishing industries of South Africa and Namibia depend on this productivity, harvesting millions of tons of fish each year from waters that, were it not for the cold Bengala current and its upwelling, would be far less productive. Looking at global ocean circulation from above, a pattern emerges that reflects the fundamental physics of our rotating planet. Gyres rotate clockwise in the northern hemisphere, from the North Pacific Gyre to the North Atlantic Gyre, each turning in the same direction due to the combined effects of wind patterns and the Coriolis force. In the northern hemisphere, the deflection to the right causes currents to curve clockwise, creating these great rotating systems. The pattern is so consistent that if you know you're in the northern hemisphere and you understand gyre circulation, you can predict the general direction of currents based on where you are within the gyre. Along the western edge, currents flow northward. Along the northern edge, eastward. Along the eastern edge, southward. And along the southern edge, westward, completing the circle. This clockwise rotation has shaped navigation routes, determined where ships sailed and where they avoided, influenced where naval battles were fought and trade routes established. The gyres are permanent features of the ocean, as reliable as the seasons, and understanding their rotation is fundamental to understanding how the ocean moves, how it transports heat and nutrients, and how it connects different parts of our planet in one continuous, flowing system. Where different currents meet, where waters of contrasting temperatures and origins converge, something remarkable happens. Clashing currents create nutrient-rich fishing regions, zones of extraordinary productivity where the ocean seems to concentrate life itself. These frontal zones, where warm meets cold or where currents from different directions collide, are places of turbulence and mixing. The clash forces water upward, bringing nutrients from depth to surface. It creates eddies and swirls that trap and concentrate plankton. Temperature differences attract different species, creating diverse communities where cold water and warm water organisms overlap. Fishermen have known for generations to seek out these convergence zones, recognizable by changes in water color, by lines of foam or debris on the surface, by the gathering of seabirds diving for fish. The Grand Banks off Newfoundland, where the cold Labrador current meets the warm Gulf Stream, have been one of the world's great fishing grounds for centuries. The Dogger Bank in the North Sea, where currents converge in shallow water, was so productive that it sustained entire communities. These clashing currents create boundaries in the ocean, edges where different worlds meet, and at these edges, life flourishes with an intensity unmatched in the more uniform waters to either side. The influence of ocean currents on coastal climates extends beyond the well-known examples of the Gulf Stream or Kuroshio. Regional currents can warm otherwise cool coastlines, creating microclimates that support vegetation and wildlife unexpected at those latitudes. The North Atlantic Drift, that extension of the Gulf Stream, bathes the coasts of Ireland, Scotland, and Norway with warmth that makes these high-latitude regions surprisingly mild. Palm trees grow in southwestern Ireland, a latitude where palms have no business surviving. The coast of Norway remains largely ice-free even above the Arctic Circle, allowing ports to operate year-round. Alaska's southeastern coast, washed by warm currents from the Pacific, supports temperate rainforests in a region that might otherwise be tundra. These regional warming effects create pockets of habitability, allowing human settlement and agriculture in places that would otherwise be too harsh, supporting ecosystems adapted to warmth in latitudes dominated by cold. The currents give locally what the latitude takes away, creating climate anomalies that have shaped patterns of human settlement and natural ecosystems for thousands of years. When scientists calculate the energy transported by ocean currents, the numbers are staggering. Ocean currents transport energy equivalent to vast human consumption, carrying more energy in the form of heat than all the power plants humans have ever built could generate. The Gulf Stream alone transports heat northward at a rate of about 1 petawatt. That's 1,000,000 billion watts, more than 50 times the total energy consumption of human civilization. This heat, drawn from tropical waters warmed by the sun, is delivered to higher latitudes where it moderates climate, prevents ice formation, and generally makes vast regions more habitable than they otherwise would be. The ocean does this work continuously, without fanfare, without fuel consumption beyond the sun's energy and the wind's push, maintaining Earth's climate balance through sheer scale of operation. When we speak of ocean currents as rivers in the sea, we must remember that these are rivers carrying not just water but energy, enormous quantities of it, redistributing the sun's warmth across the planet's surface in a grand circulation that has operated since the oceans formed and will continue as long as the sun shines and the Earth spins. The global circulation of the ocean operates on timescales that dwarf human experience. The Global Conveyor Belt takes over a millennium to complete, 1,000 years for water to travel from the surface in the North Atlantic through the depths of every ocean and back to the surface again. Water that sank during the Middle Ages is only now rising in the Pacific. Water sinking today won't see sunlight again until the year 3000. This millennia-long journey connects past and future in a way that few natural processes do, creating a deep memory in the ocean. Properties imparted to water when it sinks, the temperature, the salinity, the dissolved gases, persist for centuries as that water creeps through the abyss. The conveyor belt is patient, operating on geological time, indifferent to the human dramas playing out above. It mixed water when dinosaurs roamed the earth. It will continue mixing water long after humans are gone. Yet its timescale also means it responds slowly to change, taking centuries to fully reflect alterations in surface conditions, creating a lag between cause and effect that complicates our understanding of climate change and its impacts. Not all currents span ocean basins or persist for centuries. At smaller scales, other motions occur that are equally important for ocean function. Small-scale currents intensify nutrient mixing, creating pockets of enhanced productivity even in regions not known for upwelling. These small currents, eddies only a few kilometers across, swirls created by local topography or wind patterns, can bring deep water to the surface or mix surface water downward. They create patchiness in the ocean, regions of high productivity scattered like oases in less productive waters. A seamount rising from the depths can deflect currents upward, creating an area of enhanced mixing above it that supports unusual concentrations of fish and marine mammals. Tidal flow over rough bottom topography generates turbulence that mixes nutrients upward. Even the wake of large swimming animals creates small-scale mixing. These processes operate continuously at scales too small to see on ocean-wide maps, yet collectively they account for significant nutrient transport, supporting productivity in places where larger-scale processes alone would leave the water relatively barren. The ocean's depths are supplied not only by the slow sinking of dense water over wide areas but also by more dramatic flows through specific passages. Deep overflows feed major ocean basins, pouring cold dense water through gaps in underwater ridges, cascading downward like underwater waterfalls. The overflow from the Norwegian Sea into the North Atlantic, plunging through passages between Iceland, the Faroe Islands, and Scotland, delivers cold, dense water that becomes part of the North Atlantic deep water. Similar overflows occur in other regions, wherever dense water accumulates behind a barrier and then spills over or through it, descending to depth on the far side. These overflows are concentrated, intense, relatively fast-flowing despite their location in the deep ocean. They're the drainage points, the spillways that allow dense water to find its level in the global ocean. Without these pathways, circulation would be much weaker, the oceans more stagnant, the mixing of properties between surface and deep much slower. The overflows are essential components of ocean circulation, connecting surface and depth through focused flows that pack enormous transport into relatively narrow passages. Between the wind-driven surface waters and the deep cold waters of the abyss lies another realm of circulation. Intermediate waters spread from southern oceans, flowing at depths of several hundred to 1,000 meters, carrying properties acquired at the surface in high southern latitudes to regions thousands of kilometers away. Antarctic intermediate water, formed where surface waters sink around the Antarctic convergence, spreads northward into all three major ocean basins, sliding beneath warmer surface waters but remaining above the denser deep waters. This intermediate layer is remarkably widespread, traceable by its distinctive temperature and salinity signature across much of the world ocean. It represents another pathway in the ocean circulation, another way that water mixes and properties spread. The ocean is not simply a two-layer system of surface and deep, but a multi-layered structure with distinct water masses at different depths, each with its own circulation, each contributing to the overall mixing that prevents the ocean from becoming stratified and stagnant. These intermediate waters are middle children of ocean circulation, less famous than surface currents or deep convection, but essential to the three-dimensional structure of the global ocean. The great boundary currents that race along the western edges of ocean basins don't just circulate within their own basins, they link distant regions in direct exchanges. Western boundary currents link distant basins, carrying water from one region of the ocean to another in directed flows that maintain connections over vast distances. The Agulhas current retroflex, sending rings and eddies westward into the Atlantic, carrying Indian Ocean water around the southern tip of Africa. The Indonesian throughflow connects the Pacific and Indian Oceans, flowing through the complex passages between Indonesian islands, the only low-latitude exchange between ocean basins. The Bering Strait provides a connection, though relatively small, between Pacific and Arctic. These inter-basin exchanges are crucial for maintaining the global conveyor belt, for allowing properties from one ocean to influence another, for creating the truly global circulation that connects all the seas. Without these linkages, each ocean basin would circulate more independently, their properties would diverge more strongly, and the ocean would be less effective at moderating global climate. The western boundary currents, strong and fast though they are, serve as more than just regional features. They're the highways connecting different parts of the global ocean in a network of exchange. The seafloor is not smooth and flat but crossed by ridges and dotted with seamounts, creating barriers and channels that guide deep water flow. Deep passages connect ocean circulation systems, allowing dense water to flow from one basin to another, maintaining the continuity of deep circulation. The Vima Channel in the South Atlantic allows Antarctic bottom water to flow northward, carrying the coldest water on Earth from the Southern Ocean into the Brazil Basin. The Romanche Fracture Zone, a deep gap in the mid-Atlantic ridge near the equator, allows bottom water from the Western Basin to flow into the Eastern Basin. These passages are often narrow, sometimes only tens of kilometers wide, yet they carry enormous volumes of water. They're the arteries of the deep ocean, the pathways that prevent any basin from becoming completely isolated. When oceanographers want to understand deep circulation, they pay close attention to these passages, measuring the flow through them, tracking how water properties change as they pass from basin to basin. The passages are natural laboratories for studying deep ocean processes, places where flow is concentrated enough to measure directly, revealing the otherwise invisible circulation of the abyss. Some of the most dramatic flows in the ocean occur not across open basins but through narrow channels where dense water pours into the depths. Dense waters cascade into the deep ocean through narrow channels, descending slopes in concentrated plumes that can flow at surprising speeds for deep water. When water becomes dense enough to sink, whether through cooling, salt rejection during ice formation, or evaporation, it doesn't spread gradually downward but rather flows along the bottom toward the deepest available depth, following the contours of the seafloor. These cascades can be intense, almost river-like in their concentration, flowing down continental slopes and through submarine canyons at speeds of tens of centimeters per second, fast for deep water. The cascading water entrains water from above as it descends, mixing and changing properties, delivering oxygen to the deep and stirring the stratification. On the Antarctic continental shelf, where sea ice formation rejects salt and creates extremely dense water, cascades pour down the continental slope, some of the densest water in the ocean plunging toward the abyssal depths. These cascades are seasonal in some places, episodic in others, but wherever they occur, they're dramatic demonstrations of density-driven flow, gravity pulling heavy water downward through channels carved in the seafloor, feeding the deepest layers of the ocean with water that last touched the surface perhaps only days or weeks before, still carrying with it the signature of the atmospheric conditions under which it formed. Along coastlines around the world, a particular danger lurks that catches swimmers and beachgoers by surprise each year. Rip currents are narrow, fast-moving surface channels that cause many drownings, pulling unwary swimmers away from shore in concentrated flows that can overwhelm even strong swimmers. These currents form when water that has been pushed toward shore by waves needs to return to the sea. Rather than flowing back evenly along the entire beach, the return flow concentrates in narrow channels, creating jets of water moving seaward at speeds that can reach several feet per second. A person caught in a rip current finds themselves being pulled away from shore despite their best efforts to swim back. The natural instinct is to fight the current, to swim directly toward the beach, but this exhausts even the strongest swimmer. The key to surviving a rip current is to swim parallel to shore, escaping the narrow channel, then swimming back to land outside the rip's pull. These currents are visible if you know what to look for: a gap in the breaking waves, a line of foam or debris moving seaward, perhaps a difference in water color. But many swimmers don't recognize the signs until they're caught, and panic can quickly set in as the shore recedes. Rip currents are reminders that even in shallow water, even on calm days, the ocean remains powerful and dangerous, its currents capable of overwhelming human strength in moments. The engine that drives much of the ocean's deep circulation is not wind or tides but simple physics. Density differences cause warm salty water to sink beneath fresher cold water, though it seems paradoxical at first. Warm water is less dense than cold water, all else being equal, and fresh water is less dense than salty water. But when water is both warm and very salty, as in the Mediterranean or the Red Sea, it can become dense enough to sink even beneath colder but less salty water. This creates a layered structure in the ocean, with different water masses stacked according to their density, the densest at the bottom, the lightest at the top. In the North Atlantic, the Gulf Stream brings warm, salty water northward. As it releases heat to the atmosphere and cools, its high salinity makes it dense enough to sink, initiating the deep convection that drives the Atlantic's overturning circulation. In other regions, cooling alone is enough to make water sink, but salinity plays a crucial role in determining exactly how dense water becomes and whether it will sink at all. The interplay of temperature and salinity creates the complex vertical structure of the ocean, with water masses at different depths distinguishable by their properties, each telling a story about where and when they formed. When we compare the ocean to the atmosphere in terms of heat transport, the ocean's dominance becomes clear. Ocean currents move heat far more efficiently than air, carrying vastly more thermal energy in their flows than winds carry in theirs. Water has a much higher heat capacity than air, meaning it takes far more energy to warm a given volume of water than the same volume of air, and conversely, water releases far more heat when it cools. The ocean can store heat through its entire depth, not just a thin surface layer, giving it an enormous reservoir of thermal energy. When currents move this water, they move all that stored heat with it. A cubic meter of seawater carries more than 4,000 times the heat energy of a cubic meter of air at the same temperature difference. This is why ocean currents are so crucial to climate. The Gulf Stream alone carries more heat northward than the entire atmospheric circulation over the Atlantic. The ocean is the primary mechanism for redistributing solar energy on our planet, with the atmosphere playing a supporting but secondary role. Understanding ocean heat transport is essential for understanding climate, both its current state and how it might change as the ocean warms and its circulation potentially weakens or shifts. The cold currents that flow from polar regions toward the equator carry more than just frigid water. Cold currents transport icebergs into lower latitudes, carrying these frozen mountains of fresh water sometimes hundreds or even thousands of miles from their origin. Icebergs carve from glacier in Greenland or Antarctica, plunging into the sea where they're caught by the prevailing currents and carried along, melting slowly as they drift into warmer waters. The cold Labrador Current carries icebergs from Greenland southward along the coast of Canada, sometimes reaching as far as the shipping lanes off Newfoundland. It was one of these icebergs, carried by the Labrador Current into the North Atlantic shipping routes, that sank the Titanic in 1912. Antarctic icebergs are sometimes even larger, some the size of small countries when they first break free, drifting in the Antarctic Circumpolar Current or being carried northward by branches that reach toward South America, Africa, and Australia. These icebergs are hazards to shipping, but they're also fascinating features in their own right, floating mountains of ice thousands of years old, containing water that fell as snow long before civilization began, now slowly returning to the sea as the currents carry them toward their eventual melting. The ocean and atmosphere are coupled systems, each influencing the other, and sometimes small changes in ocean currents can trigger cascading effects that reshape weather across entire continents. Changes in currents can trigger major climate events like El Nino, a phenomenon that demonstrates how ocean circulation and atmospheric patterns interact. El Nino begins when the trade winds weaken across the tropical Pacific, allowing warm water that has piled up in the western Pacific to slosh back eastward. This eastward movement of warm water is fundamentally a change in ocean currents, a weakening of the equatorial currents that normally flow westward. As warm water spreads across the eastern Pacific, it alters atmospheric pressure patterns, shifts rainfall, changes wind patterns, and creates weather anomalies across the entire Pacific basin and beyond. What starts as an ocean current change becomes a global climate event, bringing drought to some regions and floods to others, affecting fisheries, agriculture, even the number and intensity of hurricanes in different basins. El Niño reminds us that the ocean and atmosphere are not separate systems but parts of a coupled whole, where changes in one inevitably affect the other, sometimes with profound consequences. Not all ocean circulation occurs in the open waters of the Great Basins. Enclosed seas form looping current systems, mini-circulations contained within the boundaries of nearly landlocked waters. The Mediterranean Sea has its own gyre, a counterclockwise circulation that flows eastward along North Africa and returns westward along the European coast. The Baltic Sea, the Black Sea, even large bays like the Gulf of Mexico, each has its own characteristic circulation pattern, shaped by the basin's geometry, the winds that blow over it, and the exchanges with the larger ocean through narrow connections. These enclosed sea circulations are like smaller versions of the great ocean gyres, but confined and intensified by the surrounding land. They create predictable patterns of flow that affect everything within the basin, from navigation to fisheries to the distribution of pollutants. The enclosed seas are natural laboratories for studying ocean processes, simpler systems where cause and effect are easier to trace than in the complex open ocean, yet still displaying the fundamental behaviors that characterize all ocean circulation. The ocean does more than circulate water and heat, it also plays a crucial role in the global carbon cycle. Oceans absorb a significant portion of human-produced carbon dioxide, taking up roughly a quarter of the CO2 we release by burning fossil fuels. This oceanic uptake occurs as carbon dioxide dissolves in seawater, particularly in cold waters where gases are more soluble. Ocean currents play an essential role in this process, carrying surface water that has absorbed CO2 into the deep ocean where it can be stored for centuries. Without this oceanic uptake, atmospheric CO2 levels would be significantly higher than they are, and climate change would be proceeding even faster. But this service comes at a cost. As the ocean absorbs CO2, it becomes more acidic, affecting marine organisms that build shells and skeletons from calcium carbonate. The currents that transport heat and nutrients around the globe also transport this absorbed carbon, distributing it throughout the ocean, determining where it's stored and for how long. The ocean is a vast carbon reservoir, and its circulation controls how effectively it can continue absorbing the CO2 we release, making ocean currents not just important for climate through heat transport, but also through their role in the carbon cycle. The global ocean is not truly global in the sense of being freely connected everywhere. Narrow straits control water exchange between oceans, acting as bottlenecks that limit flow and create distinct conditions in different basins. The Strait of Gibraltar, only 14 kilometers wide at its narrowest point, controls all exchange between the Mediterranean Sea and the Atlantic Ocean. The Bering Strait, even narrower at about 85 kilometers, controls exchange between the Pacific and Arctic. The straits connecting the Red Sea to the Indian Ocean, the Baltic to the North Sea, even the passages between Caribbean islands, all serve as control points where relatively small amounts of water flowing through create disproportionate impacts on the basins they connect. In these straits, currents can be particularly strong as large volumes of water try to pass through restricted channels. The currents through the Strait of Gibraltar, for instance, are complex, with surface water flowing in one direction and deep water in the other, creating a two-layer exchange as less salty Atlantic water enters the Mediterranean at the surface while denser, saltier Mediterranean water flows out along the bottom. These strait currents are critical components of global circulation, determining how different basins interact, how properties spread between them, and ultimately shaping the character of ocean circulation worldwide. Along coastlines, The properties of seawater can vary dramatically over short distances, creating gradients that affect marine life and human activities alike. Coastal salinity varies widely due to current influence, with different currents bringing water of different salinities to the same general region. Where rivers discharge into the ocean, salinity drops, creating brackish conditions that extend offshore as far as currents carry the fresh water. Where ocean currents bring salty water from the open sea close to shore, coastal salinity remains high. The Baltic Sea has very low salinity due to high river runoff and limited exchange with the saltier North Sea. The Red Sea has very high salinity due to intense evaporation and limited circulation. Along many coasts, currents create a patchwork of different salinity regimes, each supporting different communities of organisms adapted to those specific conditions. Estuarine species that tolerate or require brackish water occupy one niche, while fully marine species occupy another. The currents that determine salinity distribution thus also determine which organisms can live where, structuring coastal ecosystems according to the water properties they deliver. At the highest latitudes, where sea ice forms each winter and melts each summer, the ocean is undergoing a transformation that affects circulation patterns. Melting sea ice alters currents by changing water density, adding fresh water to the surface ocean when ice melts, making the water less salty and therefore less dense. This freshening of surface waters can strengthen stratification, making it harder for surface water to mix with deeper layers and potentially affecting the sinking that drives deep ocean circulation. In the Arctic, where sea ice extent has decreased dramatically in recent decades, the increased melt adds significant fresh water to the Arctic Ocean and the seas surrounding it. This fresh water must go somewhere, and as it spreads southward carried by currents, it can affect deep water formation regions in the North Atlantic, potentially weakening the overturning circulation that depends on dense water sinking. Around Antarctica, similar processes occur, with ice shelf melting adding fresh water that can affect Antarctic bottom water formation. The ice, the currents, and the water density are all linked in feedback loops that we're only beginning to understand, making the polar oceans regions of particular concern as the climate continues to warm and ice continues to disappear. At the equator, where trade winds blow consistently from east to west, surface waters are pushed steadily westward across entire ocean basins. Equatorial currents pile water against continents, feeding major streams that then flow poleward as boundary currents. This process creates a literal hill of water in the western Pacific, where sea level is measurably higher than in the eastern Pacific due to the accumulated water pushed by years of westward flow. This piled-up water must go somewhere, and it feeds the Great Western Boundary Currents, the Kuroshio and the Gulf Stream and the Brazil Current, sending them racing poleward with the momentum of an entire ocean basin behind them. The equatorial currents are thus not isolated features but the first step in a chain of circulation, gathering water from across thousands of miles of ocean and delivering it to the boundary currents that will carry it toward higher latitudes. It's a continuous process, wind pushing water westward, the piled-up water flowing poleward, completing the circulation loop that forms the Great Gyres. The equator is where it begins, where the consistent trade winds create the persistent westward flow that sets everything else in motion. The deep circulation of the ocean operates in a realm far removed from the wind and waves of the surface, yet it moves with inexorable power. Thermohaline circulation moves slowly but carries enormous momentum, transporting vast quantities of water through the abyss at speeds measured in centimeters per day rather than meters per second. Slow as it is, this circulation involves such immense volumes of water that its momentum is tremendous. Once established, Thermohaline circulation patterns persist for centuries, resistant to change, creating a stability in deep ocean properties that contrasts with a more variable surface. The sluggishness of deep circulation means that changes propagate slowly through the system. Water that sinks today won't reach the far side of an ocean basin for decades or centuries. Properties imparted at the surface persist for generations as the water creeps through the depths. This slow circulation acts as a climate memory, storing and transporting heat and carbon on timescales that span human history, creating a system with tremendous inertia that responds gradually to forcing but, once set in motion, continues for ages. When we look at ocean circulation from a global perspective, certain structures dominate the view, organizing the flow into recognizable patterns. Gyres create circular flow patterns across ocean basins, the fundamental organizing principle of surface circulation. Each major basin has its gyre or gyres, great wheels of water hundreds or thousands of kilometers across, turning steadily year after year. These gyres are driven by the wind patterns of the atmosphere, the trade winds near the equator, the westerlies at mid-latitudes, combined with the Coriolis effect that deflects moving water. The gyres are not perfectly circular but elongated, compressed on their western sides where the boundary currents flow fast and narrow, stretched on their eastern sides where flow is broader and slower. Between the subtropical gyres lies the equator with its own distinctive circulation. At higher latitudes, subpolar gyres turn in the opposite direction, creating a complex global pattern of interconnected circular flows. Understanding gyres is fundamental to understanding ocean circulation, for they are the largest coherent features of the surface ocean, the structures within which smaller eddies and meanders develop, the framework that organizes the ocean's movement. As water flows westward in the equatorial currents, it doesn't simply move across unchanging conditions but accumulates heat along its journey. Equatorial currents warm as they encounter continental barriers, having crossed thousands of miles of tropical ocean where the sun beats down relentlessly. By the time equatorial water reaches the western side of a basin, it's been absorbing solar energy for weeks or months, warming several degrees above its starting temperature. This warm water, trapped against the continental barrier, becomes the source for the western boundary currents, which carry this accumulated tropical heat poleward. The warming during the westward journey is crucial for the ocean's heat transport. If water flowed directly poleward from the eastern side of basins, it would be cooler, less effective at moderating high-latitude climates. Instead, the detour westward across the tropics allows maximum warming before the poleward journey begins, maximizing the heat transport and the climatic impact. The equatorial currents are thus not just transporters but accumulators, gathering solar energy across vast distances and concentrating it for transport to higher latitudes. The ocean circulation is not truly separable into surface and deep components, for the two are linked in essential ways. Deep circulation relies on wind-driven surface processes, particularly the upwelling and surface currents that complete the circulation loop. Without wind-driven upwelling bringing deep water back to the surface, the sinking that forms deep water would eventually deplete the surface ocean and circulation would cease. The wind drives not just surface currents but also the upwelling that allows water to return from depth, maintaining the overturning circulation. In the Southern Ocean, where the strongest winds on Earth blow unimpeded around Antarctica, vigorous upwelling brings deep water to the surface, completing the circuit that began when water sank in the North Atlantic. The wind and the density-driven circulation are partners, not competitors, each essential to maintaining the other. Surface processes set up the conditions for deep water formation by transporting water to regions where it can be cooled or made more saline. Deep processes store and transport heat and carbon that affect surface conditions. The ocean circulates as a whole, surface and deep, linked in feedback loops that create a single integrated system. In specific locations around the ocean, dramatic events occur that create some of the most important water masses in the deep sea. Overflow channels create deep water masses, places where dense water formed in marginal seas or on continental shelves spills over sills and descends into the deep ocean. The Denmark Strait overflow, where dense water from the Nordic seas cascades over the sill between Greenland and Iceland and plunges down the continental slope, creates one of the densest components of North Atlantic deep water. The flow through this narrow passage is intense, a focused stream of cold water pouring downward, entraining surrounding water as it descends, mixing and transforming as it falls. Similar overflows occur in other locations, each creating water masses with distinctive properties that can be traced thousands of miles from their formation site. These overflow channels are critical choke points in global circulation, places where relatively small changes in the overflow could have disproportionate impacts on ocean circulation downstream. They're monitored closely by oceanographers seeking to understand how deep water formation might change as climate warms and conditions in the source regions shift. The currents that organize the ocean circulation also organize its pollutants, concentrating human waste in predictable locations. Plastic particles concentrate where currents converge, particularly in the centers of the subtropical gyres where Ekman transport pushes surface water inward, creating downwelling zones where floating debris accumulates. These garbage patches are not solid masses but regions where microplastic density is elevated, sometimes dramatically so. The plastic arrives via currents from coastlines thousands of miles away, fragments breaking down under sunlight and wave action into smaller and smaller pieces, but never truly disappearing. The currents that once distributed larvae and nutrients now distribute bottle caps and fishing nets, demonstrating that ocean circulation connects all parts of the sea, for better or worse. The plastic concentration in gyres is a visible manifestation of current patterns, an unintended tracer experiment showing where convergence zones lie and how long it takes for floating material to accumulate there. It's a sobering reminder that the ocean circulation, which has sustained marine life for eons, now also concentrates humanity's mistakes, creating regions where plastic threatens the ecosystems the currents once only nourished. In the darkness of the deep sea, where no sunlight penetrates and photosynthesis is impossible, life nevertheless thrives in surprising abundance in certain locations. Hydrothermal vent ecosystems thrive near current systems, the currents bringing oxygen and larvae to these isolated oases of life on the seafloor. The vents themselves pour out superheated, chemical-rich water from within the earth, and bacteria that can metabolize these chemicals form the base of a food web independent of the sun. But these ecosystems don't exist in isolation. Currents sweep along the seafloor, bringing oxygen that vent organisms need, carrying away the chemical-rich plumes that can be detected miles downstream, and most importantly, transporting larvae from one vent field to another. Without currents, each vent would be an island, and when a vent went extinct, as they eventually do, its unique species would disappear with it. The currents create connectivity, allowing species to spread from vent to vent, maintaining populations across regions, enabling colonization of new vents when they open. The deep sea currents, barely moving compared to surface flows, are nonetheless vigorous enough to transport larvae and maintain genetic connections across the abyss, making possible the surprising diversity and persistence of vent ecosystems. When we compare ocean currents to the rivers that flow across continents, the ocean's currents often emerge as more powerful. Some currents rival major rivers in speed and volume, matching or exceeding even the mightiest terrestrial flows. The Gulf Stream, the Kuroshio, the Agulhas, these currents transport more water than the Amazon, the Mississippi, and all other rivers combined. They flow at speeds comparable to large rivers, several miles per hour in their fastest sections. Yet unlike rivers, which are confined to valleys carved by erosion, ocean currents flow through a fluid medium, able to meander and shift, to spin off eddies, to vary in strength and position. They're rivers without banks, defined only by differences in water properties and the balance of forces acting on them. These oceanic rivers are features of planetary scale, moving water quantities that staggers comprehension, carrying heat and nutrients across thousands of miles, connecting ecosystems and climates in ways that terrestrial rivers, confined to their watersheds, never could. The ocean's rivers are the mightiest flows on Earth, and we live on a planet shaped more by their influence than by any rivers on land. Over the long spans of time that characterize biological evolution and ecological processes, ocean currents have enabled one of the most important patterns in marine biogeography. Ocean currents enable global species dispersal over decades, carrying organisms from one region to another in journeys that can span entire ocean basins. A lava released from a reef in the Caribbean might, through a series of current connections, eventually reach the coast of Africa. Seeds from mangroves are carried by currents to colonize distant shores. Even adult organisms, rafting on floating debris or in the hulls of ships, are transported by currents to new homes where they may thrive or perish depending on conditions. Over decades and centuries, these dispersal events accumulate, creating biogeographic patterns that reflect the structure of ocean circulation. Species distributions show the fingerprints of currents, with related organisms found on shores connected by favorable flows, and barriers to dispersal evident where currents divide or where water properties change too abruptly for larvae to survive the crossing. The currents have shaped life in the ocean, determining which species live where, enabling evolutionary radiations on isolated islands that received colonists via rare current-borne arrivals, creating the global patterns of marine biodiversity we see today. The ocean circulation is not just a physical phenomenon but a biological one, the framework within which marine life evolves, disperses, and diversifies, connecting all the seas in a network of flowing water that carries life itself across the planet.